Hello everyone, welcome to my post session. Here I want to introduce you our recent progress on a nucleosome calling package that is able to characterize nucleosome positions and types. So to start, as we know, nucleosome is the basic packaging unit of the chromatin. In the past studies, people usually use extensive amino acid digestion to provide nucleosome positions genome-wide. In those studies, people usually found around the transcription start site there exists a region completely free of nucleosome, which is called nucleosome-free region, in short NFR. However, in recent years, there are some other studies use different nucleosome profiling methods, including low-dose amino ChIP-seq, MPE-seq, and chemical cross-linking. In those studies, they found in so-called NFR region defined by extensive amylase digestion, there actually exists a special type of amylase-sensitive fragile nucleosome. The fragile nucleosome usually exhibits two important features. The first one is fragile nucleosome usually protects shorter DNA fragment under low amylase digestion. Secondary, fragile nucleosome can resist high amylase digestion. So given the proximity of fragile nucleosomes to transcription start site, it is very important for us to understand their biological role genome-wide. Unfortunately, currently available nucleosome calling packages are not able to distinguish fragile nucleosome from canonical nucleosome because they usually assume each nucleosome protects the 147 base pair DNA fragment, which is not compatible with fragile nucleosome property. So to resolve this, we developed a new nucleosome calling package called size-based expectation maximal, in short SEM, that can distinguish nucleosome types by protected DNA fragment lengths. So how we do that? First, we get the overall fragment size distribution of amnesic dataset. Then we apply the Gaussian mixture model to this distribution to get the fragment size distribution of each individual nucleosome type. Then combined with nucleosome common matrix including the nucleosome dialocation, occupancy, and fuzziness. Through the expectation maximal, we can compute the probability of each amnesic fragment assigned to each individual nucleosome, then use all this information to infer the nucleosome matrix and, most importantly, its type. After developing this package, we compare SEM to other existing nucleosome calling packages on common nucleosome matrix. So in terms of the dial location on both simulated and real data, two SEM runs with different occupancy threshold all achieve comparable performance to dampers and puffin. And on occupancy and fuzziness, SEM also does comparable job to dampers and puffin. All these results shows that SEM can precisely predict the nucleosome common matrix. And the most important feature of SEM is that it's able to distinguish nucleosome types. So we apply SEM to low amylase chip H2B dataset to see if SEM can successfully identify the fragile nucleosome. SEM found three different nucleosome types on this dataset. According to their protected DNA fragment lengths, we call them as short fragment nucleosome, canonical nucleosome, and dinucleosome. As we can see here, the distribution of short fragment nucleosome around transcription start site is very similar to previous reported fragile nucleosome. Since short fragment nucleosome share a similar distribution pattern as fragile nucleosome, we want to further to check if short fragment nucleosome also have very high amylase sensitivity as fragile nucleosome. To do that, we use the log ratio of number of reads on the low amylase digestion versus high amylase digestion as a proxy of amylase sensitivity. Surprisingly, we found that not all short fragment nucleosomes have high amylase sensitivity as fragile nucleosome. Short fragment nucleosome inside open chromatin generally have very high amylase sensitivity compared to canonical nucleosome, which is exactly the same as fragile nucleosome. So we call this subtype as fragile nucleosome in downstream analysis. While short fragment nucleosome outside open chromatin, they share exactly the same amylase sensitivity pattern as canonical nucleosome, but they still protect shorter DNA fragments, so we call them as non-canonical nucleosome in downstream analysis. We further explored what kind of a factor could be associated with fragile nucleosome, and we found that there are several common remodelers, including CH6, CH8, and EP400, they coexist with fragile nucleosome. As we can see from here, CH6, 8, and the EP400 are more enriched around fragile nucleosome compared to canonical nucleosome. Also, in terms of the cis-structure elements, we can find that fragile nucleosome is more frequently intersected with promoter-like elements and enhancer-like elements compared to canonical nucleosome, which potentially suggests the fragile nucleosome could participate in gene regulation. So in summary, we developed a new nucleosome calling package, SEM, that can precisely predict the common nucleosome matrix. Secondary and most importantly, SEM can distinguish nucleosome type, and SEM successfully identifies short fragment nucleosome on lower MNase chip-seq data, and they can be further divided as fragile nucleosome and non-kinetic nucleosome by integrating the attack-seq data. And finally, fragile nucleosome associated with several complementary models genome-wide and could potentially be involved in gene regulation. I want to thank all the funding support and thanks for your listening. If you have any questions, please post that on website and I will be happy to answer all of them. Thanks.